All right, welcome back. Today we're going to cackle a really cool tool from multivariable calculus, the total differential. Think back to Calc 1. You know how you use derivatives to approximate change in 2D? Well, we're going to take that same idea and blow it up into 3D. Let's jump in.
So you've probably gotten pretty good at finding a tangent line to a curve, right? And using it to estimate how a function changes. But what happens when life isn't a simple curve? Imagine you're actually standing on the side of a hill, a really complex, lumpy surface, and you take a small step forward and maybe a tiny step to the right. How much did your elevation just change? That's the exact puzzle we're here to solve.
But before we can leap into 3D, let's, do a quick rewind. We got to go back to single variable calculus for a second and dust off our memory of the differential in 2D. Trust me, this is the bedrock for everything we're about to do.
Yeah? You remember this guy, dy equals f prime of x dx. What's it really saying? It just tells us that if we take a tiny step dx along the x-axis, the approximate change in our function's height, that's dy, is basically just the slope of the tangent line right at that spot, multiplied by how far we stepped. It's an estimate for sure, but a darn good one for small changes.
Okay, warm-up's over. Now for the main event. We're going to take that simple, beautiful idea and launch it straight into 3 dimensions. This is where we finally meet the total differential.
So here it is. This is our workhorse formula. dz is our estimated change in height, our altitude. But now instead of just one derivative, we've got 2 partial derivatives doing the work. fx tells us how fast we're changing in the x direction, and fy tells us the rate of change in the y direction. We're just adding up the little bit of change from our step in x with the little bit of change from our step in y to get the total estimated change. Makes sense, right?
Okay, that formula is great and all, but what does it actually mean? What are we looking at? Let's get a picture in our heads, because this is where the whole concept is going to click into place.
So just imagine our function is this, a curved blue sheet or a hill. If you actually walk from one point to another on that surface, the actual honest-to-goodness change in your height, we call that delta z, is the change you feel as you walk along that curve. It's the real exact value.
Now, the differential, dz, is playing a different game. It's not measuring the change on that curvy, complicated surface. No way. It's measuring the change in height on the tangent plane. Think of it like a flat sheet of cardboard that's just perfectly balanced on our surface at our starting point. This plane is the best flat approximation of the surface right there. So we're using something simple and flat to estimate something complex and curved.
Okay, so here's the big takeaway. Delta z is the real deal, the exact change, but it can be a real pain to calculate. dz, on the other hand, is our approximation. It's calculated on that super simple tangent plane. It's just an estimate, yeah, but as we're about to see, it's often an unbelievably good one.
All right, that's enough theory. Let's get our hands dirty and see how this thing actually works. We'll kick things off with a pretty straightforward example, just finding the total differential for a function.
So let's take a look at this function here. A surface defined by z equals x squared y cubed. Our only job right now is to find the general formula for dz, the total differential. This is the formula that's going to let us approximate the change in z anywhere on this surface.
Okay, let's walk through it. First up, we need the partial derivative with respect to x. So we pretend y is just a number, and we get 2xy cubed. Easy enough. Next, we do the same for y, pretending x is a constant. That gives us 3x squared y squared. And now for the final step, we just slam them into our total differential formula, and bam, we're done.
So finding the formula is cool and all, but the real magic of the differential is actually using it to estimate stuff. So let's move on to our next example and see where this really starts to get powerful.
Okay, here's the scenario. We are standing at the point 2, 1 on the surface given by z equals x squared plus 3y. We're about to take a tiny step to a new point, 2.05, 0.96. Now, our goal is to estimate how much our height changed without having to plug those messy new numbers into the original function. We're going to take a shortcut.
First things first, let's gather our ingredients. The change in x, our dx, is just 2.05 minus 2, so that's 0.05. The change in y dy is 0.96 minus 1, so that's a negative 0.04. Got it. Now for the partials. The partial with respect to x is 2x, and at our point 2, 1, that's just 4. The partial with respect to y is even easier, it's just 3. Okay, we've got everything we need.
All right, now we just plug and chug. We take our formula.
dz equals the partial fx, which was 4, times our dx of 0.05, then we add the partial fy, that was 3, times our dy of negative 0.04. You do that little bit of arithmetic, and what do you get? An estimated change of 0.08.
And now, the moment of truth. How good was our little shortcut? Our differential dz gave us 0.08. Now, if you actually go through the trouble of calculating the real change, delta z, you get 0.0825. I mean, look at that. They're practically the same number. And that right there is the magic of the total differential. We used way simpler math. We didn't have to square 2.05 or anything, and we got an answer that is so close to the real value, it's amazing. This is exactly why it's such a go-to tool in applied math, in physics, in engineering.
Okay, so this is cool for math class, but where does this stuff actually matter out there, in the real world? Well, one of the most important places is in figuring out how tiny measurement errors can snowball into huge errors in your final calculations. We call this error propagation.
Let's set up a real-world problem. Imagine you're in a workshop. Maybe you're manufacturing something. You measure the radius and height of a cone. But look, every measurement you take has a tiny bit of wiggle room, right? Some uncertainty. In this case, let's say there's a possible error of just 0.1 centimeters in each measurement. The big question is, how much could that tiny little slip-up affect the final volume you calculate? So we all know the volume of a cone depends on two variables, the radius and the height. And since the error in our volume is going to depend on the errors in both r and h, well, this sounds like a perfect job for the total differential. We're going to use dv to get a really good estimate of the maximum possible error in our volume. So, the process is the same. We take the volume formula, we find the partial derivative with respect to r, then with respect to h. Then we plug in our measured values for the radius and height, and we plug in those potential errors for dr and dh. We run the numbers through our dv formula, and the result? The maximum potential error in our volume is about 52.36 cubic centimeters.
Whoa, just let that sink in for a second. A measurement error so small you can barely see it, we're talking 1 single millimeter in both the radius and the height, can combine to create a potential error of over 52 cubic centimeters in your final calculation. That just goes to show you how incredibly sensitive some calculations can be to even the tiniest initial mistakes.
And that really leaves us with a final thought, doesn't it? We saw this happen with a simple cone, but start thinking bigger. What about calculating the trajectory of a billion-dollar spacecraft? Or mixing a life-saving drug? Or designing a bridge that thousands of people will drive on every day? Understanding how these little errors can stack up, it's not just some homework problem. It is absolutely critical. And the tool you just learned, that's the fundamental way engineers and scientists analyze that risk.